Blessed is the man who does not walk in the counsel of the wicked, or stand in the way of sinners, or sit in the seat of mockers, but his delight is in the law of the Lord, and on his law he meditates day and night. He shall be like a tree planted by streams of water, which yields its fruit in his season. His leaf also does not wither, and whatever he does prospers. Not so the wicked. They are like the chaff which the wind blows away. Therefore the wicked will not stand in the judgment, nor sinners in the assembly of the righteous. For the Lord watches over the way of the righteous, but the way of the wicked will perish. Okay, everybody, we are talking about 69B, which is on your, quiet please, determinants. Okay, we started this one yesterday. We're going to work a couple of problems with 69B, and you may stop whistling, please. And then we're going to move on to the normal curve, okay? So that'll be 70. Here we go. When we're talking about determinants, remember A, B, C, D. Whenever we have a determinant, all we're going to do is cross multiply AD minus BC. And that's our very simple formula for a 2 by 2 determinant. Okay, so we use determinants in problems, all right? So if I had a problem like this, I would know I need to cross multiply those, and then equal that. So let's do it. When I multiply these two together, I can FOIL them, right? What will I get?
X squared plus 6x plus 8.
Very good. And then I'm going to take that and subtract what? 15 equals negative 5. Okay. Yes. Very quickly. So now when I finish this, I'm going to get what? X squared plus 6x minus 7 plus 5
minus 2.
Okay? So now when I go to solve that, is there a way to factor that?
Yes. No.
Yeah. It's not, well, I could complete the square and I would get a what? I would get an answer, so let's go ahead and do that. So on this one, we did do it right? Minus 7 plus 2. So we got that right. So let's go ahead and complete the square since this does not have a factor. X squared plus 6x, and that'll put my 2 on the other side. I'm going to cut my 6 in half. 3, square it, get 9. Add 9 over here, right? So I've got x plus 3 quantity squared is 11. And then x plus 3 is what? Plus or minus the square root of 11. And then x is negative 3 plus or minus the square root of 11. Okay, and that one was the example, and that's what they got. Okay, so that one is the answer for that one. Now look over here too. This was just another example they gave. One more. We're going to multiply this way, multiply that way, always subtracting that second one. So we get
4x plus 16 minus 6 equals 18.
Okay, this one is not quadratic, so let's isolate. That's a 10, so we're going to go over there. It's an 8. X is equal to 2. And notice if we plug this back in, we'd get 6, and we'd get 24 minus 6 is 18, and it works. Okay, so now we're going to move on to the normal curve, which is less than 70. So we're going to change this to less than 70. And we're going to start just briefly introducing your standard normal curve here. We're going to start out with a normal curve. Okay, and the normal curve looks like a pile of sand. Okay, because if you did dump a large quantity of sand on the beach, guess what it would make? A normal curve. It's a natural tendency for large pieces of data to fall in this distribution. Mine's not quite perfect. Yours in the book is better. Okay? But there's some things about the normal curve that we can know for certain. Okay? There's certain things that we can count on. All right? Science has shown that when a distribution like this occurs, and it occurs naturally in a lot of things, like I say, if you dumped a pile of sand that was loose flowing, and it had the ability to settle down. It would settle down in a normal curve, all right? And we could put some numbers to that, okay? So what we're going to talk about the normal curve here is that there is a probability, okay? Underneath the curve is the probability that each part of this is going to happen. Altogether, the probability is 1. In other words, the data is going to be under the curve somewhere. Now, these parts of the curve never ever touch. They approach asymptotically, right, in this direction. So they keep on going, but they never ever really touch the bottom of the curve. And of course, this is going to be a 50% mark right here at the mean, okay, which is going to be the highest point. We've got 50% of our data that lies this way and 50% of our data that lies that way, okay? And then you will see on your page 441 that they have some very interesting numbers that prove true. And you can do this on a normal curve. When you get a standard chart, you will see these bear true, okay? But approximately 68% of all of our data will lie between the first and the negative first standard deviations from the mean. And that's every normal curve. If they say that a piece of data is approximately normal, it's going to work this way, okay? So we've got 68% of the data lies in between here, in between the second and the -2 standard deviation. We're going to have what percentage? 95% of all of our data will lie within those. And then between the -3 and the 3, 99% of all of our data lies within those. Okay? So basically, look at the top of the page here. All right? When they're doing this, okay, look at the top of the page. So they're saying, we're talking about when we use standardized test scores, down there at the bottom of that paragraph, we compare the scores of individual students to the scores of millions of students, okay, who have taken the test previously. This is called norming a test. When they norm a test, they figure out how all the students do on it, and they adjust the mean of that test. They figure out what is the standard deviation of that test so that then they can make those predictions. Once they find the standard deviation, they say, okay, well, 68% of all the data has to lie within those two regions there, okay? So they're showing you that in the middle of the page. Down at the bottom, they're talking about the 50 percentile, okay? And we talked about this before. Since we know it is symmetrical, that if this is 68% in here, this in here is going to be approximately 34% and approximately 34%, right? In here, because this is approximately 95%, and you take away the 68%, 95 minus 68 is what? 27, and you divide that in 2, right? You will find out what's in each one of those. So that's going to be what, 13.5%? 13.5% here and 13.5% over there. Then I've got 2, because I got 99 minus 95 is 4%, and then I split it. So I've got approximately 2% of my data lies in there. 2% of my data. And then out here, I've only got 1 percentile left unaccounted for. So it's 0.5% out there, and over here, 0.5% over there. Okay, so that's how your data is spread. Because we know how the data is spread, we can make predictions of what's going to happen with your data. Okay, so if I were going to talk about the population of Niceville, and I said it is approximately normal. Once they say that, then you can apply all of these percentages to it. Okay, so if I said, okay, the population is approximately normal, and the mean age of of Niceville is 45, okay, and the standard deviation is 5, then you would know if the mean was 45 and the standard deviation was 5, then between, 40 and 50, I've got 68% of all my people in Niceville will lie between 40 and 50 years of age. Okay, so once I say it's approximately normal, I can do all kinds of predictions and data searching on it because I know what that means to be approximately normal. Okay, so look over here. They're talking about a standardized test on page 442 there. Okay, now they're saying there's very nice, you don't want to memorize that formula up there, but that formula up there is the formula. It says we show the equation for the normal curve on the left. All right, we can use this equation and a calculator to show that the total area under the normal curve is 1. All right, so you don't have to use that formula. You don't have to memorize that formula because basically they've taken that and they've done that a lot and they've put it in a standard normal table for you to be able to access. So when you see the standard normal table down there, right, they have used this formula a bootcoodle times and they've gotten all this data from this formula. So you don't have to go to the formula. You can use the standard normal table down here, which will make it much nicer. Okay. Now, they're saying, okay, what we want to do is, so we got this data. We've got all this data and say we're using this data for Niceville, population of Niceville. So my mean is 45 and my standard deviation is 5 steps to the right. So this is going to be 50, my one, negative 45, 40, right? Okay, what they're talking about here is, wouldn't it be nice to be able to compare data from one population to another population, all right? And that's why they created the standard normal table. This normal distribution here has a mean of 45 because it's my Niceville, okay? But what they're talking about, the standard normal table, is when I decide that the mean is going to be 0 of every population. I'm going to standardize it. I'm going to call 0 my mean. I'm going to say this one standard deviation will be 1 to the right, 2 to the right, 3 to the right, -1, -2, -3. When I go to a standard normal distribution, I basically take all of this data and I shift it over into a new standard. And once I have this for the city of Niceville, because its mean is 0 and my standard deviations are now standardized, I can compare data from Niceville's population to Crestview's and Fort Walton Beaches and Destin's because I have the data standardized, okay, with a mean that every standard normal curve is going to have a mean of 0. So I can start to compare data between different data collections, okay? So that's what they've done. And they said, all right, we're going to find a standard score. And this is where they found on this little test thing, they have Zoli's score, okay? Zoli's score, and this is her standard score. And this is going to tell you X minus mu over standard deviation. All right, so this z-score, this standard score that they're talking about, this whole testing scenario here, is a z-score. And basically the z-score is how many standard deviations from the mean are you? Okay, so basically when you're talking about being able to compare data, all right, you want to know not how many standard deviations on this graph you are from the mean, because this normal table and Crestview's normal table and Fort Walton's normal table and all the different cities around us would be very hard to compare because they would have different means and they would have different sizes of standard deviations. okay? But if we normalize them, we put them on a standard, we got the z-score, then we could use one and compare them all, okay? So the benefit of a z-score is that we can translate data from a specific mean and standard deviation to a standard normal curve where they would actually all mean the same thing, okay? So basically, we're going to play with this a lot when we're like comparing two different tests, okay? So suppose you made a certain mean, you were in a history test and there was a certain mean and standard deviation of that history test, okay? Then you went over and you took an AP physics test and there was a certain mean and standard deviation to the physics test. And you wanted to know which test did you do better on, because they were close enough that you wanted to know which one you really did better in the scheme of things. You would standardize both of those scores and you would put them on a z-score, a standard normal table. So let's play with some z-scores here. Okay, now they're taking this whole thing and they're saying, okay, Zoli, and they started this on the other side, okay, so they said Zoli made a 150, no, she made a 171 on a test whose z-score, she made a 171, and the mean, you gotta go. Welcome one second. The mean was 150, okay, and the standard deviation for this test was 10. Okay, and she wants to know where she stands in the big scheme of things. Okay, how did she do on that test? So she says, okay, I made a 171. I know I'm higher than the mean, but how good is that score? Okay, so she does the z-score and she plugs in the 171. That's what she made on the test, 171. Okay, and then she plugs in the 150. That's the mean of the test. That's what everybody averaged. And then the 10 was the standard deviation of the test. So when she subtracts, she gets 21 on top. She divides by 10. She's got 2.1. Okay? That means that she is at the 2.1 mark over here on the z-score. Okay? That means at what percentile is she approximately? Okay, well, remember the 99 goes from here to here, right? But when you look at it, you say, okay, well, I know, can you figure out about where she is just knowing this right here? Okay, she got in between here and here was 95% of the data, right? 95% of the data, but how much of the data above here? Okay, so remember 95% of the data in here, but I can get on a z-score chart and I can go to 2.1. That's what they're showing you down here. You can get it pretty exactly right here. You go down to 2, you go across to 0.1, and she's at 98.21% of all the people that have taken that test. She's at 98.2% of all the people that have taken that test. That's pretty good. Okay? So you can compare your data with somebody else's. Okay? Now, when they do something like the SATs, okay, they have to re-norm these tests periodically because the norms change. All right? The averages change over the course of time. And they have to make new tests, right? And then they have to re-norm those tests. They have to say, okay, what is my new average? What is my new standard deviation so that I can compare everybody in this data, okay? So you can go to the chart with these. All right, if you didn't have the chart to go to, you could have done what? You could have said, okay, in between here and here, right, this one was 95% of the data. So to the right here would be what? 47.5? 47.5 up until this mark. Now I can't go to that one very easily without my table over there. But then I could say what? 50% of the data was over here. So 50 plus 47.5 would be 97.5. And we didn't even account for this little 0.1 over here, because that's what we need to go to the table for. But we can still get a pretty good estimate. She was at 97.5% without even taking that 0.1 into account. Yes?
I don't understand how you got 47.5.
Okay, basically there's 95% of all the data that lies in between these 2 and -2. And she's at 2.1, but I'm just doing it up to 2 because I'm just trying to get a rough guess, okay? So if I take that, remember it's symmetric, and I take that and I cut it in half, and it's 47.5. So this part right here, to the right of my halfway mark, is 47.5% of all the people. But then you add the 50% that lies to the left, and she's at 97 plus percentile. Which, when we do it on the table, we take into account that little 0.1 that's there. She got 98.2 percentile. Yes.
What does that mean? Like 98.
98.2% of all the people that took the test made less than she did.
Oh, maybe less than.
Okay, so basically it's a very, very good score. No. Well, she would be at the 98th percentile. Okay, that's what that means. When you're at the 98th percentile, that means that 98% of the people scored below you. Okay.
So does that mean she's in the top 98.2%?
Well, she's in the top 2%, isn't she? She's in the top 2% of all the people that have taken that test. All right. Huh?
Technically 1.8%.
All right, so everybody, let's look at a problem. Let's look at number 70.1. Shh. Okay, it says, the mean weight of the babies born in a metropolitan hospital for 7 years was 6.8 pounds. So that is our average, our mu, okay? And then it says, with a standard deviation of 0.8 pounds. Standard deviation is 0.8 pounds. Okay? Then it says, if the distribution of weights were approximately normal, that's key, they have to tell you that, what percent of the babies weighed less than 6.4 pounds? Less than 6.4 pounds. Okay, now when you look on the standard normal curve, when you look in this Z-score chart here, this standard normal chart, all of the percentages lie to the left of the mark. Okay, so whenever I find anything, I'm talking about the area under the curve to the left of whatever spot I'm at. So basically that 98.2 percentile is talking about 98.2% of all the data lies to the left of her score. So she was better than 98.2% of all the data that came in, all the test scores, okay? So now, how are we going to do this? 6.4 is the mark that we're looking for. But this is not a standardized score, is it? This is just a weight. This is the mean. Remember, if we wanted to find the Z-scores to be able to go and look at this chart, we have to find the Z-score using this formula up here, right? So we're going to say the Z-score is X minus mean over standard deviation. So let's find the Z-score for this data so that we can find out where this is lying on the standard normal curve. So 6.4 is our X. All right, so we're going to put 6.4 there, and our mean was 6.8. All right, are we going to get a positive number or a negative number?
Negative.
Negative number, which means we're going to be on the left side of the curve. That makes sense, though, when you realize 6.8 is the mean. Right? 6.8 is the mean, and 6.4, of course, would lie to the left. All right? So now we've got this one, the standard deviation was 0.8. So we've got negative 0.4 over 0.8. Okay, so when I multiply by 10 and I multiply by 10, I've got what? Negative 1/2. All right, negative 1/2 standard deviations. All right, so the Z-score is negative 1/2, which means that I'm going to get my little standard normal curve chart down here. And I'm going to say it's negative 0.5. Isn't that what
Yes.
negative 1/2 is? So I'm going to go to my, notice on your standard normal table, everybody down at the bottom of page 442, notice that they've got a positive 0 and a negative 0. All right? Because you're going in two different directions there. So we're going to go to negative 0.5. So we're going to follow the negative 0 chart down to the 0.5, and we get 0.3085. 0.3085. That is a percentage. That is a percentage of the data that lies to the left of that mark, 6.4. So what do we have? 30.85% of all the babies lie below the 6.4 pound mark. Okay? So, what are they asking? It says thus about 30.85% of the babies weighed less than 6.4. Okay? So you find that on your chart. Okay? Now let's look at number 2. As you're working with this, you need to realize that the data that you get out of the chart, that little percentile will always be to the left. So if they ask you for a percentile that lies to the right, what are you going to have to do? 1 minus the percentile that you see on the chart. If you're looking for the percentile that lies to the right, you're going to have to make that adjustment, because what's the total percentile under the curve? 1. Total is 1 underneath there, okay? 1.00. So that's 100% is 1, right? So here we go. Let's do number 2. For example, 70.1, what percent of the babies weighed 6 pounds, between 6 pounds and 7 pounds? These are fun. Between 6 pounds and 7 pounds. Okay, my little science mathematicians. How am I going to go about getting the percentage of the babies that weighed in between two different numbers? If each one of my scores on the normal chart gives me what lies to the left, okay, would I be able to find what is the percentage that lies to the left of 7 and then subtract from it the percentage that lies to the left of 6? Does that make sense? So that I would get the percentage that lies in between. All right, so here we're going to go. We're going to change this data. This is the same. This is the same. We're going to change this to 7. Okay, and we're going to find our new z-score with 7. So we're going to say, all right, 7 goes right here, 6.8 goes right here, and our 0.8 goes right there. So now we're in the positive, okay, because 7 is greater than 6.8. So we're on the positive side of the curve. So now we're going to have what? 0.2 over 0.8, which we reduce to 1/4, but it's positive. So now that's what? 0.25 or 0.25 on our little standard normal curve. So we go over here to 0.25 and we look up on the positive 0 side. We go over here to 0.2, and basically when you have a 5, you go halfway in between the two. So we're going to say, what is the average between 0.5793 and 0.6179? Somebody do that on the calculator. What's the average in between there? You find the average between them because it's right in between.
What was it?
This one right here.
0.5986.
0.5986? It should be bigger than that.
Which ones are they?
Yes.
0.7 what?
I'm averaging between 0.5793. You guys get with me in the book. 0.5793 and 0.6179. I'm averaging between those.
Yeah, it's 0.5986.
0.5986.
Yeah.
Oh, 0.5986. Okay. Sorry about that. 0.5986. Okay, that's 7%. Okay, so then I'm going to plug in a 6 right there, which means I'm going to plug in a 6 right here. And I'm going to get a what? a negative now, right? A negative 0.8. So it's going to go to what? Negative 1. So now I go to negative 1.0 on my chart. So I'm going to go to negative 1.0, 0.1587. 0.1587. Okay, does everybody understand that this is the percentage of the data that lies to the left of 7 pounds? And this is the percentage of the data that lies to the left of 6 pounds. Okay, so then I subtract the two. All right, somebody subtract 0.5986 minus 0.1587. Okay, so you get what?
0.4399.
0.4399. Okay, and then what does that mean? 43.99% of all the babies born in the hospital weighed between 7 pounds and 6 pounds. Okay, so you can do a lot of data study with these. All right, that clock is wrong. We still have time to do one more. Let's do the next one.
It's been on that same spot.
Yeah, I know. I'm like, wow.
Okay.
I really didn't.
All right, everybody look at number 3. It says, in the same hospital, what percentage of the babies weigh more than 7.2 pounds? So we're still talking about 6.8 being our mean and 0.8 being our standard deviation. But now they're saying, how many babies are bigger than 7.2 pounds? Okay, so we're going to say, all right, we're going to have, this is our X. So we have 7.2 minus the mean, 6.8. And it makes sense that 7.2 is bigger than 6.8. So we're on the right-hand side of the curve. We're on the positive, divided by 0.8. So that's going to be 0.4 divided by a 0.8, which is going to be a 1/2. So we're at the positive 1/2. Okay, and then it says a positive 1/2. We look over here, 0.1/2, and that's going to be right at 0.6915, right? 0.5. Am I at the right spot? 0.6915. 0.6915. All right, now that's 69%. 0.15 of all the babies lie to the left, but we want to know how many babies lie to the right of 7.5 pounds. So we're going to have what? 1 minus 0.6915. That will give us the number of babies that lie to the right. When I do that subtraction, what do I get? They've got it in the book. It's 0.3085%, and then we're going to have 30.85% of all the babies are bigger than that. All Aldridge babies are that big. All my babies were. Daniel was my very smallest baby, and he was 7.8. Yep.
That's almost impossible.
All the others were bigger.
I was
My dad was 12. Whatever. I was 9.
I was 6.
All right, everybody. Shh. Now look over here. Quiet, please. Are there any questions on lesson 70? Everybody understands what you're doing with your quizzes. Everybody's doing a quiz at home. Okay, everybody look at ellipses here. Ellipses on 71. Okay, so we're going to do 71, just the first part until the bell rings. We're going to use our time here and get part of 71 in there. I know, but I've got my watch. It tells me I still. I've got about 8 minutes left. Yes.
No, it's 8 o'clock right now.
Just say
Your watch is really close.
Maybe it is. Okay, but we're going to go till the bell rings. All right, everybody look at these are called conic sections in your book. Look at the bottom of page 445. Those are conic sections. And you can, because they're slices of a cone. And you can see that a circle is going to be a slice straight across a cone, perpendicular to the axis of the cone. Okay? But what is an ellipse? How are they viewing an ellipse? A slanted slice through the cone. Okay? A slanted slice through the cone. So, it says the ellipse is the locus of all the points, such that the sum of the distances from a point on the ellipse to two foci is constant. Okay, now they have a very good picture for you at the top of page 446. Look at page 446, and they have two ellipses, two foci points here. Okay, the center of the ellipse would go right in between the two. Now, if you were to draw a point here, so we're going to make that a point on the ellipse, where the distance between that point on the ellipse and the 2 points here were the same distance. Then if you pretend this is a string, okay, so that every point on here I have to keep these two the same amount of string, then when you move this one over here, this one's got to get shorter because I used more string over here. And then when I get this one, and this is the same piece of string here, this one's got to get shorter because I have only so much string to work with. So if you visualize a piece of string, which they actually show better in the picture, okay? So your ellipse ends up being something like this, okay? Because it's going to keep on, and then what happens here? Okay, this little piece of string doubles back over, okay? And then it's going to come over here, and it's going to bounce over there and so forth, okay? So basically, but it's the same piece of string. Your string doesn't get any longer. Your string doesn't get any shorter. It's the path of those points that makes the ellipse. So the little piece of string between these two foci and every point on the ellipse has to stay the same. So as you move your pencil, and this one gets longer, this one gets shorter, and this one gets longer, and this one gets shorter, and so forth, okay? So they have the cool little picture there. Now we are going to be studying about ellipses that are of these two types. Now ellipses that are slanted do exist, but they're outside the scope of this class because they're harder to deal with. But we're going to be dealing with horizontal ellipses where the x-axis is the major axis, okay? And then we're going to deal with vertical ellipses where the y-axis or the vertical axis is the major axis, okay? So the longer one is the major axis. And then we have a standard form of ellipses. X squared and then y squared is equal to 1. And notice what they put on the bottom. Okay? They've got a squared and b squared. Peter, do we have a problem?
No, ma'am.
Okay. Now, when you're looking at these, look over on the right, page 447. Okay? They're giving you a picture of your ellipse components here. Okay, so here we've got the center of the ellipse here, and then this one here is my major axis because it's a little longer on that side. We'll make it, that's the major axis. Okay, then this one right here, this distance here is my A. Okay, and this distance here is my B. All right, then, so this right here, this point is 0B. And this point here is A0, okay? And then when I've got these little foci points here, so this is foci 2 and foci 1, okay? And you guys just stay after class, please. Okay, something's going on. I want to find out what it is, so just y'all stay. All right? And then we've got x squared over 25 plus y squared over 9 equals 1. Okay, now when we have this ellipse, then I know that my A is what?
5.
My A is 5 and my B is
3.
3. So if I were going to graph that, I would graph 1, 2, 3, 4, 5, and 1, 2, 3, and I would graph my ellipse. Okay, so you can graph an ellipse very easily if you just know what your major axis is and what your minor axis is. Take the square root of that, that's your 5. Take the square root of that, that's your 3. Okay, you guys that were cutting up, stay after.
Miss Yard.
Got him.